from Environment and Climate Change Canada is the co-chair of the session. We have decided to share the task in such a way that I would be basically chairing the operations of the conference, except for my presentation where Daniel will keep an eye on me. As you see from the schedule, we have a busy schedule. We have 15 minutes total. So that means 12 minutes for presentation, 2 minutes for question, and 1 minute for ins and outs. So the way it's going to work is that when you have 2 minutes left, I'll say 2 minutes. And when you have no time left, basically, I'll say last sentence. And if you're continuing much beyond a short last sentence, you'll be found in contravention of the rules and regulations of this conference, and I will be able to do something which is much harder to do in the real conference, which is to throw you out of the Zoom meeting, or I'll ask our technical person, Chiao Ma, to do so. I don't want to put too much pressure, but this is how this is the best way to try to maintain the schedule so that we can be synchronized with the other sessions. With this, Kian-Li, if you want to start setting up your presentation, taking the screen, and Danielle perhaps release your the display of the presentations.
Yep. Okay.
So we have our first presentation today by, is it Kian-Li? How do I pronounce it?
You're right.
I'm not hearing you, but that's my fault. Okay, go ahead.
Can you hear me all right now? Can you see me?
Yeah, that's better.
Okay.
So you're presenting the overall program of the replacement of the Canadian Weather Radar Network. Please go ahead.
Okay. And thank you, Professor Fabry, and good morning, good afternoon, everyone. My name is Qian-Li, and I'm the Science Liaison Officer with the Canadian Weather Radar Replacement Program in the Meteorological Service of Canada. So I work closely with the radar research folks from S&T branch, as well as the data processing teams from a different section of ECCC. So it's my pleasure today, on behalf of our radar replacement team, to give you an update on the progress of the project. So here's a brief outline of the presentation. I will bring you up to speed on where we are at from our last CMOS update, highlight our accomplishment, and will provide a view of our focus and timeline for the coming year. I will note some of the challenges, risks, and mitigation strategies that we continue to manage along the way. Then look ahead to the final radars to be replaced. Finally, I will touch on our project closeout phase as we approach the wrapping up of the project. So the CW Canadian Weather Radar Replacement Project has 3 phases: definition, implementation, and closeout. So the implementation phase started in 2016, and it is a 7-year infrastructure project. On the screen is a schematic of project timeline since the beginning of the project. It has taken a few years, but we are now almost to the finish line. We only have 7 radars left to be built, each with the challenges posed by the pandemic. We have successfully replaced the expected number of radars each year, and we still remain on time and under budget. So looking back in year 2021, this photo on the screen are from the 7 radar installed last year, including some major cities: Toronto, Ottawa, Vancouver, Edmonton, Halifax, as well as Georgian Bay Area. We installed a radar at a new location in Cold Lake, and this is one of the 2 radars used to be owned and operated by D&D. Now we have 26 new S-band radars completed across the country, spanning from the West Coast to Eastern Newfoundland. 25 of these are operational radars, and the last one is a non-operational radar served for training and testing. So we thought 2020 would have been the most challenging year of the project, but the last year was also very challenging. 5 radars located in high population centers that drawing significant public attention. Every slight change generates a lot of questions. So then the past fall, we were starting to take a breath. We ran into a supply chain issue and exacerbated by the BC floods. So give us a lot of hiccups. Somehow the contractor was able to bring the Cavell radar up and running in the burning phase just before the Christmas. So our team's model is max flex. Despite all those hiccups along the way, we were very glad that we made it through and we are still in good health. There have been significant improvements to radar software, data integration, data processing, and quality. So I'm sure Daniel, Yanti, and Sudesh will talk about these improvements in details through their talks. Also, we were able to decommission all the radars in the past years, and all the public and the First Nation consultation have been completed for all 7 remaining radars. The contractors also successfully completed 5 foundations last fall. So all this has been done through a successful collaboration between MSC, the contractor, different branches within ECCC, and Shared Service of Canada. We're advancing our understanding of the new radar through a better collaboration of the new radar system and a better understanding of radar signal processing through science-focused workshops. We're continuing our work to address issues such as RF interference, second trip contamination, beam blockage, and ground clutters. Last year, we also implemented a very interesting 400-meter scan strategy as a mitigation measures to fill radar coverage gap during the construction of some new radars. It continued to help provide coverage over the southwestern Newfoundland during the Marble Mountain outage. So our forecasters are very happy with the new scan strategy, and we're looking for options to increase the range of all radars before the end of the project. So this is still in discussion, and you will hear more about scan strategy topic from Daniel's talk. So more on project support to research activities. We requested the contractor to investigate a technical solution which would enable real-time parallel processing of INQ data from an operational radar system. So this request was driven by a white paper produced by Daniel's group, which identified the exploitation of raw INQ data in real time for research support purpose, recognizing the advantage of availability of moment files as output. So the system was delivered to us just a month ago. It's named as a CASPA. In addition to process the live INQ radar feed from a site, the system can replay INQ data recorded from other radar sites as well. So the system is currently being tested at a training and testing site. Once accepted, it will be installed at the King site, and it will be used for a variety of configuration tests. So this map shows where we are at. The green circles on the map really shows how far we have come in terms of replacing the radar. And the red circles indicate the 7 sites for this year. There are some significant risks that we are tracking closely. The first one is the potentially inability to meet project timeline due to some factors related to wildfires, supply chain delays, and the pandemic. So if necessary, we would seek a budget reprofile to next year if we cannot deliver it. So the risk likelihood of this is medium, and impact severity is medium as well. Another risk is the inability to complete radar tower construction within contracting authority scope. So due to the dramatic increase in the cost of steel. And CWLRP would likely need to self-contract construction activities such as foundation work if that's the case. The risk is low and impact severity is low as well. And the third one is our last radar site for seeker relocation to be replaced at Half Moon Peak. Depend on how negotiation goes with different people, different organization. So we're currently negotiating power sharing agreement with TELUS, road use agreement with Sunshine Coast Community Forest is just done. And we have another quit claim with a mineral permit holder. So depending on all those negotiations, we could seek for budget reprofile to the next year. The risk is medium and the impact severity is low. Then on the screen, there are plans for the 7 radar sites to be finished over this year. So the sites span the country from one side to the other, and each site has its own challenge. Some of the sites are on mountaintops or on a brand new location or both. So with our smaller CWRP team, we expect that it will be another very busy year. So overall, there will be less outage of existing radars this year due to construction, as 4 of the sites are in brand new location and old radars won't be impacted. But there are still 3 mountaintops site will impacted by radar coverage outage. So I'm not going to go through all the sites, but I want to highlight some of them. First one, the Fort McMurray area radar is the only expansion of the radar network. So as this is a new site, there will be no impact to existing radar coverage, but it will result in a significant expansion of the radar coverage over northeastern Alberta and northwestern Saskatchewan.
2 minutes.
Okay. Mount Apica is the replacement site for DND's La Castor radar, and the new site is about 87 kilometers to the southwest of the old one. The biggest impact is still on the Marble Mountain site, as I already mentioned it last year. So because of the footprint and the high winds in that area make it impossible to build a radar within 1 year. So talk about BC radar on this slide. The BC interior will have a construction related to radar gaps this summer. Prince George and Silver Mountain, Silver Star radars are all on top of a mountain. And the Prince George have a small footprint. Silver Star Mountain has a short build season as well. So to help mitigate the coverage gap, we have a 400-kilometer range from the nearby Alberta radar to provide some high elevation coverage. Our monitoring section will be prioritizing the availability of other networks, such as a Lightning network, upper air, and service station. We will continue to operate the old Silver Star radar if severe weather is expected during a period when there's a severe weather. And we're going to turn the radar on with a blanked sector, as you see on the screen, when there's a need. So although we can't operate the old radar 24/7, we hope that this can give some data when it's really needed. Last but not least, the final radar of the project will be Half Moon Peak on the Sunshine Coast, replacing the long defunct Mount Seeker radar on Vancouver Island. The plan is well underway for this final radar. From the map on the right, you can see that the range of this radar, which is it's a well extended low elevation coverage to southwestern BC, and in particular to the to the east coast of Vancouver Island.
Last sentence.
So that's the finish of my project. So we're working on the closeout phase. We'll hope to gather all the input from different sections together. Very important things is to identify lessons learned and get a document recorded from all the teams. Thank you.
Thank you, Tian. Questions? I think we're a small enough group that you can intervene, and if there's more than 2 people speaking at the same time, I'll decide who speaks first. So what's the biggest challenge, Ken, that's left to complete the project by January, right?
The fiscal year is by the end of March.
Okay.
The biggest challenge, I think, is still the supply chain problem, where there are some subsystem where I think is shortage. So we don't have all the radar parts for the last radar yet. And also fire is the forest fire season in BC. So these are the top challenges.
Can I ask a question about
Go ahead, George.
calibration? One of our frustrations has always been calibration and the lack of reporting on it. Are you going to provide the calibration data to everyone? Or is it just going to be an internal type document?
The radar system calibration in terms of preventive maintenance and corrective maintenance.
Yeah, all the metadata associated with the radars is really important when you come to analyze it for a case or whatever.
I think, first of all, the National Radar Program, they enter all the record in the SAP, in the subsystem. So if you have access to subsystem, you should see all the dates and the activities done for each of the site maintenance. We also have a monitoring system built, I think, from CWRP, but now we're in discussion with CSFB to transfer. You can get some of the metadata from that monitoring system as well. I think Steve Holden have access to that monitoring system.
Is that only available internally, or is it available to external users too?
Right now, it is only available internally.
Okay, thank you very much, Kian. Let's move on to Dan Michelson, who's going to be talking about how the Canadian S-band radar scanning strategy will be improved.
Thank you. Can you hear me all right? Okay, super. Thank you very much, Mr. Chair. And hello, everybody. I'd like to start by acknowledging and recognizing my distinguished co-authors. And I'd also like to note that I'm essentially carrying on from a talk I gave last year, also on scan strategy, and this time pointing the way forward to some new ideas and suggestions. Starting, however, with a review, which is to acknowledge that scan strategy is all about compromise. And for a number of different categories of applications, each will be driven by a corresponding priority. And the graphic on the right illustrates how these priorities are inherently at odds with each other, such that if we move towards improving one of them, that improvement will inevitably be at the expense of the others. So when we talk about improving scan strategy, our objective therefore becomes to identify a better compromise. So we need to keep that in mind. Also, a recap of the default operational scan strategy that we have in place today. It is a 6-minute polar volume at S-band. It contains 17 elevation angles in top-down order, where the top 11 sweeps are single PRF, 1 degree by ½ kilometer bins, and they're collected relatively rapidly. The bottom 6 sweeps are dual PRF, ½ degree by ½ kilometer data, and they take considerably longer to acquire. Now, the pros and cons of these are that, as you can see in the red sawtooth plot on the right, That's a 4-kilometer CAPI. Just to help visualize, we don't actually generate a 4-kilometer CAPI, but this is just to help understand some of the characteristics. We have some discontinuities in a couple of gaps in elevation angles, and we do have quite a bit of second trip echoes. This operational scan strategy is well tested operationally. We have good quality radial wind data, and so it does represent a reasonable baseline compromise. There's a mountain version of the scan strategy where we replace 2 low-level sweeps with 1, as is indicated in the yellow box on the right-hand side. And that allows us to introduce a very low-level sweep at minus 0.3 degrees to cover valleys. The advantage of that, of course, is that we do get that lower level coverage for nearby valleys. It comes at the expense of poorer lower level vertical resolution at or above 0.4 degrees. And there can be blockages at longer ranges, as illustrated by the simplified mountain in the graphic. Carrying on, there is a long range version of PVOL 6S as well. As Chin indicated, and in a similar way, we take out 2 low-level sweeps and replace them with 1. And that allows us to introduce a 0.3 degree sweep that goes all the way out to 400 kilometers. It's 1 degree by half a kilometer data, single PRF, and it's introduced as a temporary measure last year. The temporary is in quotation marks because we're not sure how temporary it is, and that's part of the discussion. So pros and cons, we have a long-range gap filler. We don't have a lot of second trip due to the long range of that low-level sweep. The 0.4 degree sweep arrives a little earlier because there's 1 fewer sweep above it. But, and it's operationally tested, which is important. Cons are that it does take longer to acquire this long-range sweep. The quality of the winds is very poor, and we do get a bit more clutter simply because we are lowering the elevation angle just a little bit. The files are a bit larger, and it does represent a conflict with the mountain sweep that I just mentioned. Algorithms are not tuned for this long-range sweep, and so these data are not used together with the rest of the volume. And as we'll see in a moment, we have limited ability to detect precipitation at distant ranges because the beam simply becomes too high. So now we can start looking ahead towards changes we can make. And this is a tweaked PVOL 6S, which is a step towards what we would inevitably like to achieve. What we've done here is that we've lowered 3.6 to 2.5. We've lowered 2.8 to 2.7. The sweeps above 2.7 have been redistributed. So we get a more even sawtooth in the CAPI. And we keep the same timing as PVOL 6S. Now, these changes are minor, and it's worth noting that there's a lot more we can do, and that's where we're going next. And just before moving on to the next slide, what I'm doing now is I can add timing for each of these sweeps in the plot. So just toggling between elevation angle and time. The time associated with each sweep is at the end of the acquisition of each sweep. And so you'll see as the collection goes from top down, we end up with about 12 seconds to spare before the start of the next 6-minute acquisition. So now we can start looking at extended range. And it turns out that we can extend our operational range to 330 kilometers for free because we're already doing that with the low PRF data in the dual PRF sweeps. Low PRF to 330, high PRF to around 240. That gives us dual PRF data, and for the radial velocity data, to 240, and all the other moments to 330. So pros and cons, that gives us the same timing. It extends coverage without negatively impacting data quality. It extends range with more sweeps, which is great. And it does not require us to remove any of the other lower sweeps to make room for it. It does require testing, although we have done some testing for site acceptance. The second trip issues remain, and as is illustrated by the graphic underneath the bullet lists, you'll see that from ranges 240 to 330, half the data is interpolated from ½ degree to 1 degree rays, and we do have slightly larger files. So this leads us to want to explore 330 versus 400 and the issue of detectability. And I've got a couple of cases to show. The first one is from widespread precipitation from the radar at Holyrood, Newfoundland. And what we see on the right is a plot of mean rain rate for the whole month of November 2021. The idea here is to see at what point detectability drops beyond what would be meaningful to collect data at. And as you can see, detectability drops off very quickly beyond about 200 kilometers. When we get into the grays, I think we're only getting 5% or less. And the last bullet there is probably less of an issue for trained forecasters, but extending range beyond what is meaningful can give a false impression to the public. So that's something that we're conscious of. Now, contrast this situation here with the next one, which is from the month of September 2021 on the prairies and the radar at Radisson. And this is this case here reveals deep convection and a storm in the Regina area on August 31st local time. You'll see that the storm extends in time beyond the 330 kilometer extended range. So this does give you an example of where range beyond that would succeed in detecting this type of extreme convection containing lots of hail aloft. And the following slide here shows you the difference in time between how this case was captured with the 400 kilometer long range sweep, where the left panel shows the hail areas in white just within a 320 kilometer range, and on the right they are somewhere between 320 and 400 kilometers and have reduced in strength.
2 minutes.
So this leads us to propose a 3-minute low-level sweep, and I'm going to gloss over this slide and get right into a couple of different options for acquiring these data. This is a bit like NexRAD sales, and in this first option, what we're suggesting is that we keep the upper sweeps, take out a lower sweep to make room for a replicate lowest sweep. And the blue star shows you where the breaking point would be to collect, after collecting the first 0.4 sweep, go down and then go back up, complete the volume and get the second low-level sweep. This would give us low-level coverage every 3 minutes. We'd get a bit more temporal discontinuity with some of the sweeps, and we'd get a little poorer low-level vertical resolution. So this is one way of doing it. The second way of doing it is to keep the upper sweeps and take out a lower sweep. And you'll see the timing in this case as well, and the break point between the first and the second of the replicate sweeps. So this is how things could be organized. And that does leave us with, this leaves us with Mountain, which is, using this extended range setup, it would lead us to thin out both upper and lower level sweeps. But in terms of timing, duplicate the 0.4 degree sweep, again, after about 3 minutes, we'd get the mountain version of this with extended range also for some of the higher sweeps.
Last sentence, Daniel.
The timing is there, and I'm going to jump to summary and conclusions. I can leave this up, but the top point here is the important one, that extended range represents a better compromise compared to long range. And we're looking forward to testing this and hopefully recommending that it be implemented if those tests go well. Thanks very much.
Thank you, Daniel. A nice talk. Any questions? I saw random phase flash. Any reason, given that you have a coherent radar, not to use a coherent phase, a sequence like is being done with NextRad? Because they're designed to be more efficient than the random ones. Random ones made sense for magnetron because that's all you can get. But with a klystron, you can be a little bit, not significantly, but a little bit more efficient with coded phases.
True. I mean, what we have as an option that we're exploring now with random phase is not exactly random. It's pseudo-random. So, you know, there's a replication of a number of set phases. But what we're seeing when we use it is that there's a lot of second trip that just disappears naturally. And so we get that advantage just by turning on random phase before we even configure and use the second trip suppression functionality. So our experience so far is that there's a gain in just turning on random phase.
Okay. I could follow up, but I'll let somebody else the chance first.
Okay, I noticed you mentioned algorithms early on in your talk, Daniel, and I sort of assume that's the relationship between precipitation and your radar parameters. Have you given any thought to doing some more evaluation and validation of the existing PR relationships and others?
I think it's fair to say that we're going beyond that, and that the latest generation of quantitative precipitation estimation uses the dual pole moments.
Yeah. Sure.
And so you know, that's where we're headed operationally.
Okay, thanks.
Thank you very much, Peter. And now moving on to Janty Reid, who's going to talk about processing improvements. Go ahead, Janty.
Hi, thank you, Professor. Can you see my screen and can you hear me?
I can see your screen and hear you.
Okay, thanks. Okay, well, good morning, good afternoon, everyone. My name is Janty Reid. I work for the MSE. My talk today is about updates to operational radar processing under CWRP. I'm presenting on behalf of my colleagues in MSc, Science and Technology, and Corporate Services and Finance branch. Okay, so my talk today includes a short overview of the CWRP and Radar Processing Applications Project, our project timeline, improvements and new products, and some slides and updates to our public platforms and some future work. So this is a repeat slide from last year. And just as a review, and what we heard earlier is that CWRP is a 7-year infrastructure program that will replace MSC's existing radar network with modern, new dual polarization radar systems. In addition to this, did I lose my screen? Can you still see it?
We're seeing a background,
Red.
probably, yeah.
Okay, I would say that my screen just died. Just give me 1 second while I find it again. Sorry about this. It is loading PowerPoint. I am so sorry.
The joy of technology. We always had those issues, and the variety of them is a bit different with remote presentations, but yeah.
If I can just jump in while
Okay.
your screen is loading, Yanti, we have a little over 60 people in this session now, and that's a really nice result. So I just wanted to point that out.
Wow, it's really thinking about it. I don't think I've ever had PowerPoint kind of blow up midway through a presentation, and it's really thinking about it.
Can you say a few words about your talk without slides?
Well, yeah, I was just going to give, a quick high-level timeline of what we achieved to date. And basically just starting in 2016, that the project was launched with the announcement of the German manufacturer Celix, now Leonardo, as the radars of choice. In 2017, our operational software adaptations began, first starting with the X-band, which were used as gap fillers by MSC, and then later for the radar, the S-bands themselves. The first S-band radar was deployed at Radisson in 2017, and it marked the deployment of the PVOL-6S scan strategy that Daniel talked about. And this complemented that 10-minute scan strategy by the C-bands. And then between 2018 to 2022, we methodically adapted our operational processing system called the URP in a very incremental manner. First year, we focused on sort of reflectivity products, moved on to Doppler, our severe weather algorithms in 2019. And then in 2020, we introduced the dual pole products, dual pole QPE and Parka, which I talked to last year. And DPQPE became the default radar product on our ECC public platforms back in 2020. And then we've been making incremental improvements ever since. Wow, it's really thinking about it, Fred. I really feel bad about this.
Don't be. We are feeling bad for you, but you're doing great. Please continue.
Okay. And just to say that, I'm going to talk about improvements today from 2021 and onwards. And we've also made other modifications, such as supporting the new scan strategies that Daniel talked about. We've had to make improvements to our processing infrastructure, added data processing redundancies to our environments, and also enhanced our data archiving. Oh, I feel.
Hello, Jenny.
Wow.
I'm the volunteer of this session. So if possible, you can send me your slides to me via email, and maybe I can help you to show your PowerPoint here.
Oh, sure.
Actually,
or did you want to move on to the next person? Yeah, and I can just do it at the end? Yeah. Yeah.
Yanti, Daniel here. I could share my screen with your presentation if you like.
Yeah, I can also do that.
Sure, go ahead.
Yeah.
Okay, let me see.
Just want to say I've had many places where talks have been presented, and Yanti has never screwed up before. or Yanti's computer has never screwed up before.
It literally just won't load anymore. I'm like, oh. Thanks, Daniel.
So let me see if I can.
Let's move to slide number 5. Yeah, we'll move to number 5. That's great. Thank you so much. Okay, so one of the key improvements developed by S&T this past year was dual pole QPE for snow. This work carries on from the DPQPE rain rates that we presented last year. So the long-time ECC method of estimated liquid equivalent snow rate was reflectivity based. And in this work, we use a composite S of Z and S of KDP and Z for snow liquid equivalent rates. Next slide, please. So this slide here shows the updated equations behind the QPE calculations. 1 and 2 are what we talked about last year for rain, and new are the snow algorithms under points 3 and 4, using and the current snow thresholds that we're using. So similar to rain rate, KDP is now used in snow rate estimations under certain conditions. And the key reference for this work, Bukovic et al. 2018, is also provided here. Next slide. This is a pure snow example from Blainville, Quebec in February 2021. Snow estimates millimeters per hour using the S of Z relationship is on the left, and the new composite relationships are used on the right. And you can see notable differences in the QPE with higher values using the dual pole method. We know that the threshold evaluation on this work is ongoing, and updates are anticipated in the near future. Full integration with PARCA or particle class will improve the application of proper rain rate relationships for all the relevant pixels. Next slide. A hybrid hole filling algorithm was introduced last year to DPQPE, which is based on the 0.4 scan. In this work, we attempt to address gaps which have been brought on by processing. And what we've done here is to use the pixels from the next 2 elevation scans above it to fill in the gaps on the 0.4 degree PPI. So next slide. So here's an example of the hybrid hole filling algorithm at Blainville. Left shows DPQPE without hole filling, and the right shows it with the hole filling on. The red ovals indicate that much of the precipitation has been recovered in the gaps over the mountains in the northwest of the radar and over Mount Royal in Montreal. The orange ovals indicate areas where DPQPE has removed for wind farms, echoes in the south, but not all, and the resultant holes are being filled by the upper scans. Next slide. To improve radar data quality and product quality, we have implemented a ZDR bias correction to our production chain for QPE and PARCA. Accurate measurements of ZDR are required to make the most of dual pole measurements, and accuracy within 0.2 dB is required for quantitative applications. In this work, the algorithm estimates ZDR biases using measurements in light rainfall, and an example is on the next slide. So next slide, please. This slide shows 2 ZDR PPIs. The one on the left is from Radisson, Saskatchewan. The one on the right is from Bethune, where geographically Radisson is northwest of Bethune. The radar showed different ZDR values during this widespread precipitation event in 2020. And this was due to ZDR calibration differences between the new radars. Can I get you to click, Daniel? That's great. The bottom panels show corrected ZDR PPIs, which have been corrected by 0.5 dB and the other by 0.1. So that's the result there. Next slide. This slide demonstrates the impact of ZDR corrections on particle class. This example is from Chipman in 2021. The left shows particle classification with no bias correction done. The right, it has been applied. And you can see updates to the particle class types. So on the right, we can see that some of the big drops in yellow beneath the melting layer have been turned to green, which is rain. And also we see a reclassification of some of the biological pixels in brown back to rain in green. Next slide, please. Another product quality improvement that we've added to our chain is the use of spatial melting layers in QPE and PARCA. This example is from Woodlands, Manitoba, where we now use hourly 10-kilometer resolution RDPS model data to estimate the height of the 0-degree wet bulb temperature. In this example, on the left, the warm colors of red in the southeast represent higher melting layers, while the blues and greens in the northwest represent lower melting layers, and this is basically a sloped melting layer scenario. The result is the middle, and we see kind of a deformation to our regular typical PARCA bullseye that we would see in PARCA. Here, PARCA infers more rain in the southeastern areas below the higher melting layer, and snow types in areas where the melting layer is lower. And on the right is the snow and rain relationship derived by DPQPE, and they use the appropriate relationship based on the type that we've estimated here. So next slide. Another algorithm we've improved is for vertically integrated liquid. These changes include integrating downward to the surface, similar to the US NextRad VIL algorithm. We've also introduced a maximum reflectivity cap of 56 dB, which was put in place to mitigate hail overestimation. So this is an example from Strathmore, Alberta, with the old algorithm on the left and the updated one on the right. You can see larger areas of VIL concentrations in the northwest and southeast with the new algorithms. However, the white areas, likely contaminated by hail, have been dulled a little bit. And visually, we've also decreased the minimum VIL display threshold in our internal forecast tools to remove some of the trivial values. Next slide.
Yanti, I have to remain me in 2 minutes.
Oh, 2 minutes, no problem. We've also added dual pole US NextRad level 3 products, as you can see on the screen, to complement our Canadian ones. And we'll skip along. So to the next one here. Improvements to quality control of radar data assimilation work. This QC method developed by McGill involves thresholding using the depolarization ratio method followed by a speckle filter. And these are examples of from the NextRad radar system, where echoes prone to non-uniform beam filling are removed in the first version of the QC method, but are preserved with the new QC method deployed, which is in item E. So we'll skip 2 slides and we'll go to a major achievement that we just achieved this past month, which is the migration of our 10-minute processing systems to 6 minutes. This has been rolled out internally to the ECC forecasting community first, and the 6-minute frequency now exists for the following listed products. This involved a lot of work by enabling partners such as software development, IMIT enhancements, and the coordination with our downstream clients and their applications. Next slide. The next couple of slides highlight radar updates to our public dissemination channels. First off, worth mentioning is our Open Radar Data Dissemination Project is a GO. It's a pilot project that will cover the next 6 months and test the feasibility of making radar data available to the public on a new platform called HPFX. If the pilot goes well, the next step will be opening this data as listed here to the public. Next slide. And to our public users, we have, for instance, our 10-minute composites will transition to 6-minute composites this summer or fall. We have a 1 kilometer resolution North American composite of surface precipitation types, and nowcasting will be available this fall or winter. And level 3 dual pole products will be integrated into composites by winter 2023. Keep going, one more, hopefully. This is an example of the surface particle type product from a winter storm on February 18th, which utilizes both the Parker product that I talked about and also the US hydrometeor class product and modifies the type to the surface. And it has METAR reports overlaid, and subjectively you can see that the METAR's star symbols agrees well with the blue areas, and the dots, which are METAR's rain areas, kind of agree well with the rain areas in green. And hopefully I can just pop in the last slide for future work, Daniel. Future work includes continued improvements in DPQPE, such as a bias correction in snow, continued software configuration updates, the updates that I mentioned about our public dissemination platforms, and we also have to monitor sort of our end state system performance and operational production systems. So thank you for your patience today with my IT woes. I'll be happy to take any questions.
Thank you, Yanti. One quick question. If not, we'll ask other people to ask questions on the chat as we move on to the next presentation.
Frederick, I just want to make a comment that when these radars were initially planned, it was going to be a turnkey system with no need for further development. I'm glad to see that the need for further development is being well recognized now.
Good point, George. Thank you very much. If you have other questions to Yanti, like I do, please submit them on the chat. And we're moving on to Sudesh. Sudesh, if you can share your screen and start your presentation. And Sudesh will be talking about radar observations from the Mascouche tornado. Sudesh.
Yeah, can you hear me, Fred?
I can hear you.
Okay, I'm just trying to get the screen started here. Okay. And can you see a presentation? Ahead. Okay, excellent. Good morning, good afternoon, everyone. I'm just going to run through the data that we've collected with the Blainville S-band radar for the Mascouche tornadic event, and describe some of the polarimetric variables and the signatures that we're seeing with this particular event. I'd like to acknowledge my co-authors on this as well. And just to get started quickly, because we might be behind a bit. And okay, so just to give you a quick event overview, basically on the afternoon of June 21st, 2021, a series of intense storms developed in the area surrounding the Montreal area, just ahead of a cold front. Sorry. During the entire event, 6 tornadoes were actually reported: 1 EF2, 1 EF1, and 4 EF0s, and also downbursts. And these were confirmed by NTP Northern Tornadoes Project by doing ground surveys and satellite imagery analysis across southern Quebec. NTP also performed damage surveys and confirmed the location and the observation time of the Mascouche EF2. The picture on the right here basically shows the tornado track. It started. Can you see my mouse? Yeah. Okay. Good. So the track started essentially in a field on the west end of Mascouche and basically moved northeast. The actual time, observed time, was at 1945 Z. So this basically lies sort of in between our scans, or 6-minute scanning strategy. Estimated wind speeds was in excess of 180 kilometers. The track length was about 7 kilometers, and the path width was 250. Blainville radar is essentially about 20 kilometers west of this. The actual azimuth is 77 degrees. So when I'm going to go through a series of PPI images. They're zoomed in images, basically at 1930 Z through to 1948 Z, keeping in mind that the tornado time was 1945 Z, so between that 1942 and 1948 scan. The center of the image would be, the center of the PPIs would be where the tornado track actually started. And these are all zoom PPIs for the 0.4 degree elevation scans. But before we get to that, just to give you a quick overview of what actually happened on this day. This is Mascouche here, pointed by the yellow arrow. But the cell that we're interested in, I'm just going to go back to replay the animation quickly, is this one here. It went right over the radar, and it became tornadic just after passing the radar. And as you can definitely see here, there's lots of other cells around the area that looked, more intense than the one that actually produced the tornado here. Okay, so this is just to give you an indication of our cell identification algorithm and what was going on in this particular day. This is just for one particular time scan at 1948 Z, and the far left panel here basically shows reflectivity from Blainville. All the small circles that we see here are cells that have been identified by the algorithm, and the different colors indicate the severity levels. Low severity is green, medium is yellow, and the red is high. The cell that we're actually interested in, this is Blainville right here, is actually this guy here in this yellow box. In terms of how the algorithm actually ranked these cells, this is shown in the middle panel here, and that particular cell that produced the tornado was actually ranked 5th from a number of cells that were identified on this day. We get some characteristics of the cell here as well too, but although the cell ranked 5th, we note that the mesocyclone shear was actually the highest at this particular time. The image on the right here is radial velocity at this is 2.8 degrees, and the circles that we see here, the mesocyclone detections. There's lots of mesocyclone triggering, for different cells, but essentially the mesocyclone that we're interested in is the one at the center of this particular green circle in here. Okay, so on to looking at some zoomed in PPI. Like I said, the center of the image is essentially where that track, the tornado track, started at 1940 Z, 45 Z. Blainville is indicated by the star approximately. These are raw PPIs of reflectivity, velocity, ZDR, and rho HV, well, clutter corrected reflectivity, I should say. This is at 19Z. We obviously can see it's really noisy rho HV and ZDR PPIs. Most of the strong ground clutter has been taken out for reflectivity, and you don't really see much in the velocity field. This is the same time, but I've cleaned up the data a little bit, so removed all the low reflectivity echoes that we're not interested in at the moment, and with some smoothing, we can see better defined reflectivities. You can definitely see a hook echo here in reflectivity. There are some high values in here, getting up to about 55 or 60 dBz. This is the velocity image. You see sort of a convergence line in here. The velocity is also second trip contaminated. But when we look at the ZDR images, you can see some high ZDR just at the inflow edge of the cell. Rho HV is more or less in the precipitation areas, but it's slightly lower because of the contamination with biological echoes. Moving on to the next timestamp, 6 minutes ahead now. Again, this is just the raw fields. The hook is somewhat less defined, but just cleaning up the image a little bit. Well, actually, it's still there. Velocity is still fairly noisy. And again, we see a lot of this second trip contamination here, just at where we're about to see where well, sort of indicating where the mesocyclone actually is. If you look at the upper scan at 1.6 degrees, you do have a better indication of the velocity couplet in the mesocyclone, so towards and the away velocity values. The high ZDR, you also see the high ZDR on the inflow region of the storm, and again, the rho HV is more or less diminished in that area, likely to a mix of precipitation types. Moving on to 1942 Z, and just the cleanup image again. The storm is approaching Mascouche to that touchdown that point. And again, you see lots of second trip echo contaminating the velocity field. The upper scan for the velocity no longer shows discernible rotation. What we tend to see here is in the high ZDR area, it's a bit narrower and it's a bit more curved inwards than in the previous scan. And the rho HV values are more or less the same as before. 1948. So between, like I said, between 1942 and 48 is when the tornado actually occurred, and you can still see sort of hints of rotation here, but in the velocity field. But again, it's heavily contaminated with second trip. But now we see a debris signature essentially appearing in reflectivity, a negative ZDR ball here essentially, and obviously that's coincident with the low rho HVs for definitely indicating debris in that area. Just looking at this for the upper two scans, so now we're looking at the 1.2 degree elevation for reflectivity, differential reflectivity in rho HV, and then also at 2 degrees, you can see the debris ball and reflectivities in both cases, and again the negative ZDRs and the very low rho HV indicating debris.
2 minutes.
2 minutes. Wow. Okay. So differential reflectivity, there's been lots of studies about ZDR arcs and so on, and these are usually signatures that tend to be below, around 2 kilometers or below. The idea is that with a ZDR arc, you have strong inflow, and it's causing some sort of a sorting, drop size sorting within the rotation. So you have the larger drops exhibiting higher ZDRs just at the inflow, but decreasing in ZDR values in the main precipitation areas. You don't really see it so much in these first two scans, but it's sort of exhibited more here at 1942Z, and it's pretty much overshadowed here at 1948. KDP foot signatures have also been talked about a lot in the literature. KDP is difficult to estimate in clutter and in light precipitation. The areas of KDP that we see here, the large KDP values, they match well with the large reflectivity, indicating areas of heavy precipitation. At low levels, the KDP foot is thought to be slightly behind the ZDR arc, but in this particular case, it's not very obvious. Our hydromedia classification, this is the output of our hydromedia classification for the 4 times. We see a lot of reds in here, which is indicative of hail. Some of the yellows are indicating the big drops, and of course heavy rain as well. The classes are essentially and their locations are consistent with the expectations of precip types or precipitation types, particle types that we see in tornadic cells. I'm just going to quickly go through a couple of cross sections here. I'm not going to take too much time on it. So we're just going to look at a cross section through the cell. This is at 19. We'll look at one at 1936Z. This is the cone of silence. The cell is essentially between 10 and 20 kilometers away from the radar. The top is not very high, maybe extending up to about 6 kilometers or so, but you see a high reflectivity core of hail up top, and it's coincident with a sort of a ZDR column, essentially, also extending up to about 4 or 5 kilometers or so. In the KDP, we see large KDP aloft with high Z and ZDR, and that's usually indicative of wet hail.
Last sentence.
And 1948Z, it's essentially showing more or less the same thing. And I'll just go straight to the summary slides here. It was essentially a low top supercell ecotop of about 6 kilometers. There was significant damage. There were reports of hail, 1 death, and also multiple injuries. So you can basically read the rest of this here. I'm not going to go through them all. And with that, I'll take any questions or comments if you have any.
Thank you, Sudesh. Questions?
Hey, Sudesh, it's Paul Ford here. Can you hear me?
Yeah, I can hear you.
Did you have any storm relative velocity data in CellView? I think it's in CellView, isn't it? I'm not sure.
Yes, it is in CellView. I did not, the data is available. I didn't happen to show it for this.
Oh, no problem. Yeah, thank you. We'll look at that later. Thanks.
Okay.
Any other questions?
Hello, Sudesh. It's yeah. As the chat, like maybe a high level question, like what could be done to better help the forecasters to see the signal to the noise and provide warnings at better lead time?
One of the big issues with especially tornadic events like this and circumstances where you've got a lot of cells is a second trip, and I think that there has been a lot of complaints about second trip contaminating velocity fields, especially. And really one of the first things that you need to do is to look at where that mesocyclone is, and for that you need good velocity data. So yeah, there's still work to be done.
Okay. Well, thank you, Sudesh. So my co-chair brought to my attention the fact that there was a 10-minute break. With Janti's excitement, I completely forgot about it. So this, we are going to resume talk at 1:05, so you can use that time for a short break. Perhaps we should, in parallel, while waiting, discuss a little bit how we're seeing the development in the future. So George mentioned that there seemed to be development, and that's good. And perhaps I'm going to ask Danielle, who's probably has a somewhat higher view of what's happening, higher level view. What are plans or visions that Environment Canada or his group, or maybe nobody or Hayden, have on the future of development of the Canadian radar network? Danielle?
Yeah, thanks, Fred. That's a big question, and there's a lot to unpack. I'm going to try and be as simple as I can, really. And I'm going to sound a bit like a manager, unfortunately. The limiting factor is going to be people and how much personnel we can devote to continuing to improve. And when I say improve, it can be everything from configuring and acquiring basic data to downstream data processing and more rational management of data. One really nice example that Yanti highlighted was the pilot for making data available openly, and so we'd like to be able to follow through on that and actually achieve openly available data, and that requires people to work with it. So
at the risk of sounding self-serving, there are people outside of ECCC who could help.
That's good to know, and glad to hear it. I did want to point out, though, and this is sort of where the management hat comes in, that the money runs out at the end of this fiscal year, at least for many of us who have been contributing to the project. So unless there's a new round of money somehow, somewhere, that may have an impact on our ability to continue to keep up the momentum.
Well, Ottawa is now becoming the new Moore, with like third tornado in 4 years or 5 or 6 years or so, it seems. You'd think that something like that would help the process.
Yeah.
Anybody else wants to? I mean, I'm sure Dan and I could discuss for another 5 minutes easily, and we probably will at other occasions. But while we have a bigger crowd, let's go for the wisdom. Is there anybody who wants to intervene on what would be a good idea to move forward the development on the radar, assuming we do find funding? Dominique?
Yeah, one thing is for the more downstream product, for the severe weather. In the past, it was only based on radar, but now there's more and more other sources of data, like satellite and like LiDARs and everything that can put together. So I don't know if a focus on there's a link between radar and where it goes radar to products. There might be some need to integrate better other source, not only focus on radar only severe weather.
For sure. LiDAR is relatively short range, except of course if we consider from space. Now that we have satellites geostationary that have data every 5 minutes under normal circumstance and 1 minute under special circumstance, I'm sure we could do better. George?
Yeah, I think for me, I mean, these radars were purchased for severe weather. And so that to me means automatic detection of severe weather like downbursts and tornadoes and so forth. I don't know how far along we are to actually producing products which will be automatically tell you there's a tornado likely in that area or not without going through the forecaster, because that takes time. So to me, that's a goal that should be
I mean, historically, I mean, we've had product on the Canadian side, sorry, on the McGill side that do automatic detection of some severe weather signatures, but they always have to go, or at least the feeling is in many places that trusting an entirely automatic system could be dangerous. Whether that is still true or not, I guess it remains unchallenged and to be determined. But I'm sure better, well, I don't know, Dan, if what you know about what's being, or Norm or others, what is being done in terms of severe weather detection, or at least identification to forecasters, whether there's plans for improving those.
I was just going to say it's been a holy grail for at least 50 years. And I think there are incremental steps, but it's a long way from being automatable. A dual pole gives you, better quality control, a bit better quality control. So typically the approach at EC has been to have a fairly high false alarm ratio, but basically sift out the wheat from the chaff. But when you want to actually pick out the individual kernels, you need a person to intervene. So the idea was historically the algorithms were designed to find the cases that might be interesting, so the forecaster doesn't have to look at the ones that aren't interesting. But I don't think anybody anywhere, unless I missed the last two radar conferences, but I don't think anyone has made a significant improvement in real ability to detect, say, especially F1s and F0s that we're interested in Canada. Sometimes they basically have no signature when looking for a mesocyclone, but some of the stuff that we have in Southern Ontario doesn't have a mesocyclone. So you can look for it all you want, it's not going to predict a tornado.
So what are the errors associated with the current downburst and tornado signature algorithms? How accurate are they?
Yes. Or maybe I should say no.
Well, you're implying they're not accurate, so I'm saying how accurate are they?
Well, let's say anecdotally there are a lot of misses, and there are a lot of false alarms, and there are a lot of misses. You really need a forecaster to come in and try to answer that question, but it's never been quantified. Sills and the people at Western are working on a better tornado database, which at least gives you something against you which you could evaluate. But historically, there's been nothing to evaluate against, so you really don't know except anecdotally from forecasters.
Okay, so we have a mission for the next year or two. With this, so with this, we're going to go to the next talk by Anthony Stefano, looking at evaluation of Wolf microphysics using polarimetric data. Anthony?
Thank you so much, everyone. Welcome to my talk and to the session. I'm happy to be communicating with all of you on the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh First Nations, on whose land this talk is made possible. And I also want to acknowledge all of my collaborators and sponsors, of which there are many. This is a very collaborative research effort that I'm working on, and I'm very, very excited to be sharing with all of you what it is that I do, having to do with evaluating WRF microphysics schemes during atmospheric river events in particular, using polarimetric radar data. There is a need, as we all know, to better predict extreme precipitation. Significant precipitation events are common in southern BC and the nearby US Pacific Northwest each year in winter. Numerical weather prediction models can be optimized to better predict these events using reliable observations to validate model equations and outcomes. As we can imagine, this is sometimes easier in some places than in others. In the United States, for example, where there are many, many kinds of observation sources operational at once, there are many different ways to talk about how a weather model is performing. Here in Canada, given the complex terrain, particularly in Southwest BC, but also in other areas of the country, that's not always possible. So we want to think about other kinds of observation sources, particularly and ideally spatially, that we could use to assess weather forecast model performance. Polarimetric radars have become integral for frequently observing clouds and precipitation at high resolutions. Many scientists have begun exploiting data from North America's high-density radar network to enhance microphysics schemes in NWP models, and these simulate the evolution of tiny water droplets into clouds and precipitation. The guiding questions, therefore, of my research are two. First, how frequently do accurate extreme precipitation forecasts correspond to accurate microphysics simulations? For most purposes, and practically speaking, people might be satisfied with a very high performing extreme precipitation forecast for, like, let's say, an atmospheric river event. But we hope in the NWP community that those accurate forecasts are informed by appropriately simulated microphysics parameterizations. And we know from very much literature over time that there are lots of issues that need to be worked on to make these microphysics schemes more accurate. But a second question then is, to what extent can polarimetric radar data be applied as a reliable observation source for microphysical processes? And to answer this question, I came across a very interesting and powerful software package that came out of NASA in the last 5 years, and it's called Polaris. The polarimetric radar retrieval and instrument simulator, also known as Polaris, allows for direct statistical, and I should add, spatial comparison between microphysics scheme output in NWP models and polarimetric radar data. The idea being that we can try and make the left panel, which is an output from a weather forecast model, become more accurate if we inform it based on spatially observed precipitation using radar data. So we use this in somehow to inform how this looks in the end. And this is how Polaris works. It's a basic scheme to explain. Initially, WRF and most NWP output files and netCDFs are not compatible to directly compare with radar observations. The variables are different and the file processing is very different. However, Polaris makes it possible to make this comparison by, in its first component, called Polaris F, converting WRF output into equivalent simulated radar fields. And this is, of course, using the background in radar meteorology and wave theory to convert what we know from weather forecast variables into what we would see if they were radar variables instead. And then these become easily comparable, oranges to oranges. Now, in addition, you can integrate temperature data to help inform the hydrometeor classification and Doppler velocity data to help inform vertical and horizontal velocity fields. And once you have all these together, you can now make this very direct comparison and have some post-processing and statistics computed, which can then allow us to answer the question, as we've been answering over many, many years, why do forecasts differ from observations? And now it's not only in a point sense, but also in a spatial sense. The current study looks at two case studies. One occurred on the 3rd and 4th December of 2015 during the Olympics field campaign, when an intense low pressure system brought rainfall to the Olympic mountains. Many instruments were deployed to capture this event, and by these I mean things like disdrometers, aerial surveillance, and a whole bunch of other sources, including a WSR 88D polarimetric radar called the KLGX radar, Langley Hill. A more recent study, which all of us can probably remember if we've been watching the news, occurred last year on the 13th to 16th of November, when a similar intense low pressure system brought extreme rainfall to the lower mainland of BC. And in this case, there were few instruments deployed to look at this event, but they did include the CASAG Eldergrove radar. So my idea was I wanted to pull observations from both radars and then run WRF model forecasts for each of these events to recreate them. These WRF forecasts were centered on the radars to be able to directly compare by overlay the radar observations. So on the left, we have the Langley Hill case, where the center is given by the radar, and we have multiple domains extending out from that center. Same thing for the Aldergrove study, where it's centered on the Aldergrove radar, and then we have grids out from there. The innermost radar domain for both is 1 kilometer. Now, if we want to configure these and talk about how these were prepared, for the NWP setups, it's fairly straightforward. We use WRF 4.4.2, informed by initial conditions from the GFF at quarter degree, 931 domain configuration, 400 by 400 cells in the innermost domain centered on the radars. And I looked at 5 different microscheme choices and configurations. These include the WRF single and double moment scheme, the Thomson, the Morrison, and the more recently developed P3 scheme. I studied all 5 simulations, so that combines to a total of approximately 30 simulation runs for this one case and then for the second case as well at Aldergrove. But then to create the Polaris, which ingests the NWP output as well as the observations, I also had to create a configuration for this. And this uses Polaris 4.4 on both stations again. And the simulation data is coming from the innermost domain, so the WRF 1 kilometer. Simulated frequency is the standard, so S-band about 2.85 gigahertz, and coverage up to 300 kilometers. So this is, again, simulated to compare with what the radar is actually seeing for these cases. And now we can look at some preliminary results, which are very exciting. So I'll begin with looking at what the observations look like when we run Polaris, just taking a second to load here. Oh, here we go. Okay. We'll back up one. Oh, it doesn't seem to be backing up. Oh, actually, sorry, I do have it right. Okay. So I'll start back with the previous one. Oh, my cursor's not. Oh, here we go. All right, it's misbehaving. The first panel shows an RHI across the center of the radar station. So this is a typo, it should say Y is 0 kilometers. So it's at the level latitude of this is the Aldergrove radar case now. So we're looking at the Aldergrove radar at the cross-section latitude of the radar itself during the most intense period of the Aldergrove, of the November 2021 case. And the first panel is the hydrometeor classification, as we know, informed by fuzzy logic by all the other panels at the same time. And what we can see is something that we would expect. So we see lots of rain falling to the east of the radar, some drizzle lower behind, a clear melting region indicated by wet snow, that's the WS here. And everything above is under frozen category, so either ice crystal or snow aggregate. We do see some evidence as well of some accretion from low density graupel falling down into regions and then coated by supercooled liquid water to have higher density graupel lower to the surface. But altogether, we see what we expect, including the cone of silence, which is clearly marked. Now, if we want to look at the action region where the melting layer is occurring, so all the things are all frozen or turning into liquid hydrometeors, then we can look at a CAPI at 2 kilometers at that same level. And we can see, again, a spread in the upper left corner of all the different hydrometeors occurring at that level. So we have things like wet snow, snow aggregates, AG in purple, and we have crystals in the brown here, but mostly wet snow. So we have a clear transition region occurring. Now, most interestingly, if we were to average across the 3-hour interval when the storm was at its peak, across all CAPIs in the domain in 1 kilometer, then we can actually get an idea of overall what hydrometeor distribution are we seeing associated with this atmospheric river landfall. And what we see are primarily at low levels, we have drizzle, mostly rain, some high density graupel, a central region in altitude of wet snow indicating a transition layer, and frozen hydrometeors aloft. So the question becomes, do we see this all the time? And if we do, what are our forecasts seeing? Are they seeing the same thing? And if not, does that suggest something about the microphysics scheme informing that forecast?
2 minutes.
I'm just going to quickly go over the potential because I haven't run yet the forecast version of this. But the potential of Polaris is to have this kind of comparison between the radar observations and what we see for the Morrison scheme, for example. So once converted to an equivalent radar data set, we can actually compare. And what we see are differences. And these differences form the impetus to further look into microphysics schemes and see if making those better can make the forecasts more accurate in the end. And what we see here is a clear, almost missing wet snow layer at 2 and 1 kilometer above the surface. And this is also a different case, I should say. This is for the Langley Hill atmospheric river case. So additional case studies, data from nearby sources, and further optimization of Polaris itself are required to confirm these findings. But if they hold, then so far what I've been seeing is that the melting layer seems to be an area of interest because wet snow is underpredicted by our NWP models, and that's across most of the 5 NP schemes that I've looked at. And there are many next things to do as well. So Polaris does provide a novel approach to visualizing polarimetric radar data and evaluating microphysics schemes as well. But there's more to do. I want to explore looking at a wintertime hydrometeor classification developed at CSU, because it actually includes things like dendrites and other kinds of columns as opposed to things like hail and big drops, which for these kinds of cases are not really occurring. I want to integrate other velocity data. I want to perform a precip and microphysical verification for both of these cases, which is currently ongoing, and then subset all the data to look at different sections of the storm, prefrontal, postfrontal, to look at how the atmospheric river is performing or what it looks like in different sections. And with that, I give you my thanks and I encourage some questions. Thank you so much for listening.
Thank you very much, Anthony. Questions? We have a question on the chat from Yichen Lo. Do these differences in microphysics, such as the lack of wet snow, impact the total precipitation amount?
I would argue, yes, it does. So there are many pathways in microphysics to get to the output that we see at the surface. So every process really counts. In particular, where wet snow is concerned, we have a lot of melting going on. So the transition from solid to liquid and how much of it is occurring can ultimately lead to how much rain we get at the surface. We would have to account for evaporation going on from on the way down, but generally speaking, yes, that wet snow layer does have an impact on the liquid precipitation that we then measure at the ground.
Do we have any other questions?
I've got a question for you, Anthony. Daniel here. You showed the Langley Hill versus Morrison scheme, and I'm wondering if the Morrison scheme is representative roughly for the other 4 schemes that you looked at, or whether there are any significant differences that you've already observed.
That's a great question. The wet snow missing part, the layer missing wet snow was consistent actually across all of my schemes that I've looked at so far. There were a couple of artifacts that I need to fix because they came from the summer hydrometeor classification routine. And so, like, for example, seeing Graupel above, well above where we would expect it is not physical. But generally speaking, that was a very big eye-popping moment for me to see that consistency. So yes, that one scheme was representative, particularly with the issue of wet snow across that layer.
Thank you very much, Anthony. And
Thank you so
with
much.
this, I guess it's my turn.
You're turning it over to me now, Fred?
If you want.
Okay, well, ladies and gentlemen, it is my distinct pleasure to welcome to the speaker's podium Professor Fred Fabry, and he is going to give a talk entitled Dual Polarization Radar Data at Vertical Incidence and What It Teaches Us. Please go ahead.
Thank you very much. So this work is a joint collaboration between myself and Véronique Meunier, a research assistant at the radar, and it deals with the beast on the left, which is a vertically pointing radar that we've been using to collect dual polarization data. So when we think of dual polarization radar data, we typically think of scanning radar, such as the one on the lower left, where you have a radar rotating and making measurements like above. Vertically pointing radar is more like the one on the lower right, where there's actually 2, one underneath the blue dome and one that looks, not quite sure, it looks like a very flattened can a bit further out. And basically it's a radar whereby the weather just moves overhead, and therefore what you're measuring is as a function of height. You're measuring reflectivity, Doppler velocity, whatever else, and you're able to see things like generating cells, trails. A lot of the early microphysics work were done by vertically pointing radar. Now, dual polarization radars, everybody, just in case, you send a wave horizontally polarized, you send another wave vertically polarized, and you do comparisons so you can make measurements of reflectivity, but then you cannot, like standard radars, but you can also look at differential reflectivity, the ratio of those two, differential phase, how much one is being delayed with respect to the other, and how are the signal correlated. The latter, differential reflectivity giving an idea of how flattened things are, and that copolar, basically how variable, copolar coloration, how variable are the shapes. And now, if you take a dual polarization radar and you point it vertically, you end up with a situation like this, where you've got 2 waves that essentially are horizontally polarized. And what you end up with is that there is one polarization. So if you take a radar and you imagine it's shifting up, you're going to have one polarization that used to be horizontal that's going to be in one axis. And the one that used to be vertical is, again, perpendicular, but in the other direction. So in the case of our radar that we've been using, one of them, which we will call H by convention, but it isn't horizontal, well, they're both horizontal, is along the St. Lawrence Valley, versus the V1 is perpendicular to the St. Lawrence Valley. So what can we actually see with that? With a normal, quote unquote, single polarization vertically pointing radar, you're able to get images like this. So this is time over, say, an 8-hour period. We have height, and we're able to see low-level echoes, reflectivity on top. From the boundary layer, insects primarily. We have a widespread precipitation cell with a bright band in the middle and rain below and snow above. And here we've got a few convective, tiny clouds starting to generate a few drops with a convective cell between 21 and 2200. So that's reflectivity. You're able to see Doppler velocity. Now, when you're pointing up, Doppler velocity is vertical velocity. So that gives you, 1 meter per second is snow. If it's 5 meters per second, it's rain. And if it's higher, like here, you either have a downdraft or you start to have the bigger things, possibly like small hail. That's with the normal radar. If you have dual polarization radar, you get some other information. The first one is differential reflectivity, like normal radar. Now, for weather is spherical from underneath. So from underneath, basically, you're going to see zero most of the time. Actually, all of the time. I haven't been able to find weather that looks significantly different from zero. I was hoping, but I didn't. We have insects here that, in this case, are oriented. Blue is orientation done primarily along the valley, St. Lawrence Valley, and then red is perpendicular to the St. Lawrence Valley. And so I'm going to display always ZDR in this blue and red color scheme. And then correlation of the two signals is plotted here. I'm going to use a kind of a fire color scheme where low value, so I'm plotting, in great radar tradition, I'm using a dB scale. I'm plotting 1 minus correlation and plotting in dB. What it does, and that's the value here, what it does is that it compresses the scale for low values that typically are associated with non-meteorological targets, and it leaves quite a bit of color scheme left for the weather part of the signal where we see the bright band signal, etc. Okay, start. Weather, I'm going to start with an insects. This is an example of an insect day. Over a 12-hour period during daytime, lots of insects. Why? We are here in the Montreal area. This is end of August. End of August, the insects are doing their very best to escape, and we have a good winds from the north, and they're going like gangbusters. We are seeing them in the boundary layer. We're seeing them above the boundary layer, and they're moving out. And they're moving out with an intent. Many of them are aligned along the St. Lawrence Valley, and that's why you see this blue dominated color. A few of these white patches I suspect are actually from cloud, but they could be from insects for all I know. And the red is a few from other types of insects that are moving, but for them it makes more sense to move across valley. What it nicely illustrates is that insects can migrate, especially like these on days where we have favorable winds and we see many, and they try to go somewhere. And if they try to go somewhere, well, it means that their motion is different from the winds. So that's an important lesson to keep in mind when we think of using insects for measuring winds, is that the insects are trying to go somewhere. Now, okay, this is end of August. What about other days? So this is looking On the 20th of May, June, July, I didn't have 20th of August, so I chose 24th. June 5th, July 5th, August 5th, September 5th. Over this all day, the white patches are precipitation. This is 0 ZDR. Everything that's clearly insects is clearly trying to go somewhere. Sometimes they're primarily cross valley, sometimes they're primarily along the valley, and it depends on altitude, which probably means it depends on species. But they're definitely trying to go somewhere all the time. So I have yet to find a day where insects were moving randomly. I always thought that was suspicious, but clearly I've seen observations that show that they're really trying to go somewhere. Okay, switching, we're interested in weather. Things that we see on weather with dual polarization. ZDR, not interesting because it's 0 all the time, except for data quality. Sometimes we see a signal in ZDR or ZDR behaving funny, and that's because of data quality issues. It's a correlation that is helpful, and what it allows us to detect, to see is the shape variability as seen from below. Now, if you take something that is flat or 2D or 3D, if you look at from the side, from below, it's going to look spherical. So that's not too useful. But if you have things that are 1D, then depending on which direction they're heading, they're going to have apparent different shapes. And that's what we're able to see here, is that we have higher correlation when we have fluffier or larger aggregates because they look more spherical. Both the sphericity and the fluffiness makes the ZDR variability smaller and the correlation higher. In between, you have somewhat weaker values, and then there are patches where correlation is a bit lower. This is in snow, this is above the bright band. And those are associated with needles that are growing at temperatures from -5, -10 down. The bright band is known as a signature of reduced correlation, and we see that here. And the rain below is higher correlation. The bright spot in the bottom is there's ground clutter being involved in the picture, so that confuses a bit the issue. So that's the kind of image we can get. Now, you can also do spectra. If you have a single polarization radar, you have a time series of amplitude and phase of signal. You can do a spectral decomposition, get a complex Fourier components that you do a square of to get power spectrum. So this has been used for a long time. If you have a dual polarization, now you have 2 signals of amplitude and phase. So you can do spectral decomposition of the horizontal and of the vertical signal. So you get 2 time series of complex Fourier transforms on which you can compute power for both, but you can also correlate the individual Fourier components, which allows you to get not only a spectrum of power, but also a spectrum of ZDR, not too interesting, but more interesting, a spectrum of correlation. And you can get images like these. So we have,
2 minutes.
Thanks. So we have here, over that time period, we can see the power spectrum. So this is power spectrum. You've got height here, velocity on this axis. And so we have slope that's falling slowly. We have aggregates on the first side, and then you have new needles forming. And you can see them because on the correlation, they have different correlation here associated with them. You have the bright band, and actually if you look at the bright band, you're going to notice it's double here in this particular case. And what happens is that you have a good first melting of the needles. It's not too clear in this example, but other people who have other radars are better able to detect it. And then a second signature associated with a collapse of snowflakes. So we've been having fun. We can look at, for example, thunderstorms where we've got fall speeds of 10, 20 meters per second. Some of it is downdraft, some of it is hail, and you can actually see the signature on the correlation where higher correlation associated with rain and lower correlation with faster falling hail. We have something funny, like this is a winter case where we got the snow that's trying to melt, but because the melting is incomplete, it remains a slush up to the surface. And without dual polarization, I wouldn't have been able to guess that this is slush or something. So this is the kind of things that we've been having fun, and yeah, it's interesting. And if you have more questions, I'm welcome to entertain them.
Thank you very much. That was very interesting to see. Thank you also for keeping to time. And we do have time for questions and comments. And Norman has his camera and microphone on, so go ahead.
I see a question in the chat. I don't know who was first.
Sorry, I saw Norman first, but I'll get to the...
Okay, go ahead, your boss, Norman.
How do you know the insects are going somewhere as opposed to not going somewhere? How do we know they're not treading water? They don't want to go downstream, so they have to face upwind in order to stay still. Do you know that?
No, what I mean by that is that they have a velocity of their own.
They've got a pattern of their velocity.
They've got a pattern, and they've got a pointing pattern, and they have therefore an intent.
Yeah, okay.
Which means that their velocity is different from that of the wind. That's all I'm saying.
Yeah, okay, because they could be intending to go nowhere as opposed to going somewhere. Yeah.
But I find it unlikely that they fly at 4 kilometers to go nowhere.
Maybe they're treading water. Anyway, I just wondered if you actually had some way of knowing.
No, I don't.
The question in the chat is sort of on the same line of inquiry from Mike Casey. Do you know of anybody using the signals from insects to study insect movements and behavior?
There is a whole field of radar anthropology or radar insect and bird studies. A lot of it is related to birds. And there are some people who use radars to detect insects. A lot of it on individual insects by actually putting a radar reflector on the insects and tracking it. But yeah, so for example, there have been some publicized work recently by looking at insect echoes from North American composites showing decline of insects, for example. So there are people who are using it. I'm not sure they're using it the most intelligently, but yes. But I can't say that I'm totally on top of that. Oh, of course. There's a work of mine too, where we've been looking at the spruce budworm dispersal. I can point you to a paper on that. Look for Boulanger and Fabry on spruce budworm.
I was going to point you to that.
Yeah. And for David, is it possible that some insects are birds? It's possible. Some of the very high ones that are on the top or left corner, typically the birds are migrating during the night. So some of those look a bit stronger in terms of echo and could be birds, but those are relatively weak and fairly compact in echo. So I suspect they're moths much more. So moths and butterflies, very likely. Not the smaller insects for the higher flying ones, but possibly there could be a few birds.
And just to loop back to Mike's question, I'm reminded that there is a European collaboration called NRAM, ENRAM, that you can look up that addresses aeroecology. I'm sure a large chunk of that is birds, and I'm not sure to what extent they also study insects, but I believe they do.
Yeah. I think there was a highly publicized, I don't know, maybe I'm confusing birds and insects. There was another work that looked at crossing of the La Manche, the channel by maybe it was birds in the end. Never mind.
No, I think you're onto something, because I vaguely recall that as well.
The Finns were looking at stuff crossing the Baltic between Estonia and Finland.
The Gulf of Finland.
Gulf
yes.
of Finland, yeah.
That was I think that was aphids. So ladies and gentlemen, we have reached the end of this session on radar, Canada's renewed weather radar network. It would be fun to continue, but I do understand that people have places to go and things to do. So I would like to take the opportunity, together with Fred, to thank everyone for coming to this session. I'd like to thank the speakers. Fred, do you have any last words before we round things off?
Well, we're entering into a new exciting time with the renewal of the radars at Environment Canada. It'd be great to see some new science or new applications for that matter coming out, making better use for forecasters and for other users. And between the distribution of radar data and new efforts, I think we can get there.
I couldn't agree more. Thank you very much. And with that, we can officially end this session. And thanks again to everybody, and take care.
Bye-bye. Have a good conference, everybody.